Hi everyone, this presentation goes over Chapter 31 on regression analysis in the third edition of Jacobsen's textbook, Introduction to Health Research Methods, a Practical Guide. In this chapter, you will learn that linear and logistic regression models are among the most commonly used advanced statistical techniques. Here's an outline of the chapter. Section 31.1 covers regression analysis. Section 31.2 goes over simple linear regression. Section 31.3 covers simple logistic regression. Section 31.4 covers dummy variables. Section 31.5 goes over confounding and effect modification. Section 31.6 goes over multiple regression. Section 31.7 goes over causal analysis. Section 31.8 covers survival analysis, and Section 31.9 covers cautions. So Section 31.1 goes over regression modeling. And so when you have a regression model, it's a prediction model. It is a statistical model that seeks to understand relationships between one or more independent variables and one dependent variable. And so your independent variable is also often called the predictor variable. This is usually the main variable in the statistical model that predicts the value of some outcome variable. So this could be one variable, say if you're looking at racial and ethnic differences, and it could also be multiple variables. And so if you're looking at, say, socio-demographic differences and you don't have one specific variable that you're looking at, it can be either of the two. Then your dependent variable is your outcome variable, and this is the variable that represents the output or the outcome for which the variation is being studied. So this is the disease that is being looked at or the specific health behavior. And so when multiple independent variables are included in the model, the effect of one predictive variable on the outcome can be examined when controlling for other predictor variables or keeping those other variables constant. And so it could be that you're looking at the differences between race and ethnicity and, say, adherence to 24-hour movement guidelines. So I just recently published a study looking at differences in sleep, physical activity, and sedentary behavior. And so if we just wanted to look at race and ethnicity and how that impacts 24-hour adherence, then you would have that as your one independent variable. But then if we wanted to look at other socio-demographic factors, we could also control for age and sex and education as we look at that race and ethnicity as the predictor variable. And so two of the main types are linear regression and logistic regression. Linear regression is used when the outcome variable is continuous, so if it's a ratio or an interval variable. Whereas a logistic regression model is used when the outcome is binomial, and so it is a yes or no response. And so figure 31.1 goes over some steps in fitting a regression model. So you must start with your outcome variable because the outcome variable is what is needed to know whether it's linear or logistic regression, which is step 2. Then step 3 is to select one or more predictor variables. Step 4 is to make sure that the assumptions required for the model are met, such as the different variable types or the distribution of the outcome and predictor variables. Step 5 is to choose the methods that the computer will use to determine what set of predictor variables are best when explaining the relationship between independent variables and outcome variables. And so with that, this could be a certain methodology. Say you could manually adjust for different variables, or you could follow other approaches, which I'll go over in the next slide, say having the computer run some code to add and drop variables based on some certain circumstances. Then step 6 is to examine the model for potential problems. You want to look for the best fit of the variables. You don't want to include multiple variables that are highly correlated. And step 7 is to interpret the results and consider whether they fit with a theoretical framework, if that is included with your analysis. So when modeling for regression, you want to consider a few different things. So the first thing is parsimony. And this is the principle that when two models are equally good, the one that has fewer variables should be used. And so if you adjusted for 5 variables in a model, and then you look at the model and only 4 variables are in it, and it has a similar finding, you may want to look and see and be like, hey, there may be a variable that I don't need to include. So if it's employment and income, those may be highly correlated, and so you may only want to include one of the variables. And so you may decide to drop the variable, say, with the least amount of missing data. And so when you run the regression model, it could be that you run a simultaneous regression model. And this could be when it includes all predictor variables selected by the analysis, even if they're not making a significant contribution to the model fit. And so you put all of your covariates in the model. Or it could be, say, a stepwise logistic regression model. And this is when you program the computer to systematically add or remove predictor variables to find the most parsimonious model. You can also do this manually as well. There are many different approaches to doing it. And sometimes you report in papers the different steps within the models, and sometimes you only report the final fully adjusted model. So once the results are generated, you must carefully check that the fit is valid. And some of the ways to determine whether it's valid is to look at the residuals and the goodness of fit. So a residual is the difference between the observed value in a data set and the value predicted by the model. And the goodness of fit examines how well real data match the values predicted by the model. And so there are some different statistics that come out within the outputs that will tell you the fit of the model. And so you want to have the model that has the best statistical fit. And so section 31.2 goes over simple linear regression. And simple linear regression is when you examine whether there's a linear relationship between one continuous predictor variable and one outcome variable that is also continuous. So this would be, it would be a ratio or an interval variable. So you have two continuous variables here. That's the simplest model. And so the relationship can be visually displayed using a scatter plot. And then each point of the data on the scatter plot is listed, and then you can draw a line between them. Now you also could have an ordinary least squares model. And this is a linear regression modeling approach that finds the line that minimizes the average vertical distance from each point in the data set to the fitted line. And so that's just another way of expressing the easiest, the simplest linear regression. And so figure 31.2 has an example of a simple linear regression model here. And so you can see what the outputs would look like and what it looks like on the line here. Then you have your p-values over here and your predictor variable. The p-value for the predictor variable is 0.01 there. So then we also have logistic regression, and logistic regression has a different type of outcome than linear regression. This is commonly used for case control studies, but it's also used a lot in cross-sectional studies as well. And this is where the outcome is binomial. It needs to be a yes-no response. So it could be that it's a case or not a case, or it could be that it's disease or no disease. And the predictor variables can be categorical or continuous. So you don't have to have a categorical outcome and a categorical predictor variable, your predictor variables can be either way. And so figure 31.3 goes over some examples of a simple logistic regression model and what your output would look like. For a logistic regression, our output, the main thing we want to look at is our odds ratio and our confidence interval here. And so here, if our independent variable is looking at sex, then our odds ratio here is 1.90, and then we have 1.28 to 2.84 as our confidence interval. And so since it doesn't cross 1, it is statistically significant, but then you can also see the p-value here is less than 0.05. So section 31.4 goes over dummy variables, and dummy variables are really derived variables. So these are created by recoding a variable with n responses to a dichotomous variable. And so if you have multiple different sections and you want to separate the variables out, then you create multiple different variables for one question. So if you ask people to indicate whether they had yes or no to multiple different diseases, then even though you only have one variable originally, you would set it up so that there are separate variables for each of those different diseases. And so here is a way that you can set up dummy variables. So let's say if your response to your original question was A, you said no to the first part, no to the second part, and no to the third part, then you would have them all here. Like this would be your response. A represents no to this question, this question, and this question. B represents yes to the first question, but no to this question and this question. C represents no to the first part, but one to this part and no to this part, and so forth. So you can make multiple different variables based on several different responses. So this could be I have no chronic disease. This could be I have diabetes. This could be I have hypertension. This could be that I have cancer. And then it goes on. You could have other variables that said I had diabetes and hypertension and so forth. So section 31.5 goes over confounding and effect modification. So this is when a third variable comes in. This is a variable that is associated with the exposure and an outcome, but is not part of the causal pathway of the exposure to the outcome. So some third variables can conceal or muddle the true relationship between independent and dependent variables. And they may make the association between the exposure and the outcome appear more or less significant than it truly is. And so a confounder is that third variable between the exposure and the outcome that distorts that relationship. It's not considered a causal factor of the disease and is not part of the causal pathway. And so if you adjust for something, you can adjust in the regression models, and then you would say that your results are adjusted for the specific confounder. Then when you do that, there's also some Mantel-Hansel weighting that goes on typically within the, say, logistic regression modeling approach. And this is the adjusted odds ratio or other measure of association for an exposure and an outcome after that third variable is there. And that can be used to stratify the data. And so an effect modifier is when that third variable is in there and there's a different response and you want to have some sort of specific separation between the two. So when you want to see if something modifies the relationship, you would stratify the results. If you want to see if sex moderates the relationship between age and cognitive impairment, you would separate the results and have differences in the comparisons between age and cognitive impairment among males and females. And so to be a confounder or an effect modifier, it must be independently associated with both the exposure and the outcome. The measure of association should be calculated for the full population, but then also separated for each level of the third variable. You can also do a Breslow day test, which is a stratum-specific measure of association for the different comparisons. And this is used to assess the homogeneity of the stratum-specific measures of association. So when you've separated by those groups there. If the stratum-specific measure of the association is not different, but is different from the crude measure of association, then the third variable is considered a confounder. And that's when you would want to report the adjusted measure. But if the stratum-specific measure of associations are different from one another and also different from the crude measure, then it's likely to be an effect modifier. And this is when you would report stratum-specific measures. But if everything is similar, then neither confounding nor effect modification is occurring, and that's when you would report a crude measure. So this again is just something to kind of come back to in the future if you're looking at analyzing and controlling for other variables. So figure 31.5 actually goes over confounding and effect modification, and it goes over how these different variables can be presented and how it affects the results by confounding, effect modification, and no effect. So you can also have an interaction which is very similar to the effect modification, and this occurs when the effect of one predictor variable on the outcome depends on the presence or absence of a second predictor variable. So two exposure variables together have an additive or a multiplicative impact on the outcome variable. And so synergistic interactions increase the disease risk beyond the expected level, and antagonistic interactions decrease the disease risk to below the expected level. And so you can have interaction terms that are added to regression models to clarify the relationships between the set of variables, but I would caution this because they're hard to interpret. And so usually when there's an interaction, I go the effect modification approach and I will stratify the results because I think it's just easier to understand. Then some other terminology here. We could also have strenuous variables, and this is a third variable that produces an apparent but false association between two other variables that are not causally related. You could have a spurious association, and this is when results that are false or invalid are generated by extraneous variables. And you could also have what's called a lurking variable, which is a third variable that was not measured in a study, but is affecting the apparent association between the exposure variable and the outcome. So section 31.6 goes over multiple regression. And so when you have many different variables, so when you want to include multiple different variables in your regression model, it's considered multiple regression. And so you can have both continuous and categorical predictor variables in a multiple linear regression model, as long as the responses to the categorical variables are expressed by numbers and all of the key assumptions of this type of the model are met. And so that's why I always suggest anytime you have your data from your survey, you always change it to numbers right away because you can't really run a lot of statistical analysis without it. Figure 31.6 goes over examples of multivariable analysis approaches for testing relationships among three or more variables. And so you can do multiple linear regression, as we just showed, multiple logistic regression. Multiple logistic regression has that nominal outcome variable versus the continuous variable for multiple linear regression, discriminant or canonical analysis. And so independent variables in a multiple linear regression model must have reasonably independent errors. And so you want to look for multi-collinearity or autocorrection that may make the results inaccurate. And so Multicollinearity is a problem that occurs when two or more predictor variables in the multiple regression model are highly correlated. And so the redundancy makes the coefficients of one or more of these variables highly inaccurate. And so you always want to make sure that if you have variables that measure similar things, that you don't include all of them. Autocorrection is the pattern in which a variable measured over time has values influenced by its own past values. And then we have the VIF, or the variance inflation factor. This should be small enough to show that independent variables in a regression model have reasonably independent errors and are not intercorrelated. And tolerance, which is the inverse of the VIF, so 1 over VIF, and it should not be too close to 0. Then finally, we have the residuals, and the residuals for all variables must be normally distributed, and they help determine whether there is homoscedasticity or heteroscedasticity. And these really are differences and similarities in the variance among the variables. So homoscedasticity is similarity in a linear regression model, and the heteroscedasticity is the difference of the variance in the linear regression model. And so figure 31.7 goes over an example of a multiple linear regression model with two continuous variables. And here you can see the differences and the p-values there. Then figure 31.8 goes over an example of a multiple linear regression model with one continuous and one categorical variable with no interaction. So you can see the differences there. And then figure 31.9 goes over an example of a multiple linear regression model with one continuous and one categorical variable with an interaction. And so the interaction here is showing the line crossing there. So then we also have hierarchical models or multi-level models, and these are models that adjust for different levels of exposure, such as both census tract and county. It could be that you use a theoretical model for this. So I've used the Anderson's model of health behavior before, where you have predisposing factors such as age and sex, enabling factors such as education or access, and then need factors such as having a health condition. And if you look at multiple different questions and then you look at each of those separately but add them onto each other, that's a hierarchical model. Then you could have a multiple logistic regression model, which has multiple different relationships between several different variables, but without one nominal outcome variable. So I do a lot with multiple logistic regression model and nominal outcome variables, looking at presence of disease. And so figure 31.10 goes over an example of a multiple logistic regression model output. And here you could see that if your sex is your independent variable, then there's no difference because it crosses over the one. But if your variable is looking at whether a participant ate a certain food, then you have a statistically significant difference because it doesn't cross one here. So section 31.7 goes over causal analysis. So this is really just some additional terminology to be familiar with. The presence of a statistical association between two or more variables is not proof that a causal relationship is present. So correlation does not equal causation. So it's just important to always use the term association when comparing two different variables. You cannot say causation unless you can say that the relationship shows that the exposure directly causes an outcome, and that would only be valid in an experimental study. A causal factor is an exposure that has been scientifically tested and shown to occur before the disease outcome and contribute directly to its occurrence. Then we have temporality, which describes the timing of events, and Jacobsen talks a little bit about how that impacts causality, associations, and determining whether or not it's a causal factor. Now, temporarily really is important because you can't have an independent variable that is measured after a dependent variable. And so, for example, I've done several studies looking at patient-provider communication and different interactions between patients and providers over the past year, and then whether or not that influences screening. And so if you ask someone if they've had a mammogram in the past 2 years, but then they ask them about their communication with their healthcare provider in the past year, then that's a temporality issue. You can't show that there's an association between an independent variable in the last year and then a dependent variable that could have occurred before that. And so when you think about that, we have the Bradford Hill criteria, which also has a more recent adaptation such as the Hill-Dahl criteria. But this is a set of conditions that provide support for the existence of causal relationships. And so you want to have these in mind when thinking about different associations and looking at your independent variables and dependent variables and how they're related. So things like temporality, strength of the association, specificity, consistency, and other types of evidence. So you don't have to have all of these things, but it's important to consider them. So figure 3111 goes over criteria for causation, and these are the Bradford Hill criteria. And so you can go over these different questions that you should think about when determining your outcome and your independent variables. And so just a couple other things to consider when deciding what variables to select. So the etiology, so the cause of the disease or health disorder. You don't want to compare things that wouldn't necessarily be related to the disease or outcome. You should also consider multi-causality, and this is the causal pathway in which many different risk factors or combinations of risk factors contribute to the disease occurring. And in order to look at these factors, one way that you can do that really is to look at a logic model. And this is a visualization of the hypothesized causal pathways that leads to an outcome of interest. And so this is just similar to a DAG or just a theoretical framework where you put different things in different places to kind of determine the relationships and determine where those causal pathways occur. Then you can also have a recursive model, and this assumes that all causal pathways are unidirectional. Path analysis, a recursive causal analysis strategy that uses regression models to examine causal patterns among variables. You could have a non-recursive model, which assumes that causal pathways can be bidirectional. And then another more advanced statistical concept is structural equational modeling. And this is a non-recursive causal analysis strategy that can be used to examine the complexities and directions of the different paths. So section 31.8 goes over survival analysis. And so this is a different form of regression and a statistical evaluation of different endpoints from the start of the study. So it doesn't have to be death. It could just be a different well-defined event, discharge from hospital, or some other outcome. The most common population level measures of survival include median survival time, and cumulative survival at set times after enrollment or diagnosis. So say if you're diagnosed with breast cancer, depending on the stage, your 1 year or 5 year survival rate is going to be different. And so with survival analysis, we calculate things like cumulative probability, which is the probability of an event occurring by the end of a particular observation period. So you may be thinking, what percentage of people born in the early 1900s lived to 95, versus a conditional probability, which is based on some event occurring given that a prior event has already occurred. So you would say something like, what percentage of people who have already lived to the age of 90 would survive at least 5 more years to age 95? So that would be a much different probability because you're taking people who are already age 90 and then seeing how long they'll live. And survival analysis can be calculated using life tables, Kaplan-Meier plots, or log rank tests, and there's also regression analysis later. A life table is an actuarial table that displays conditional and cumulative survival properties in a population. A Kaplan-Meier plot is a time graph that displays cumulative survival rates in a study population. And a log rank test is the statistical test that determines whether survival rates are longer in one population than another. And so here's a good example of a Kaplan-Meier plot. And so the x-axis here is years, and then the cumulative survival here is on the y-axis. And so you're starting off with 100%. At the first year, since no one has died, then it's 100% survival. And then as people drop off, the survival rate at year 1 has gone down to about 85%. And then survival rate at year 3 is 55% here. And so when you do a regression for survival analysis, you use a hazard model or a Cox proportional hazard regression. And so the hazard function is what's listed in an equation, and we haven't gone over a whole lot of equations for regression within this textbook, but as you go further on in your studies, you may be asked to write these. A hazard ratio is very similar to an odds ratio or risk ratio, but it compares the duration of time to an event in two populations. And then if you look at that as a regression analysis, you would use the Cox proportional hazard regression model. So section 31.5 goes over some cautions. And so this chapter has gone over a lot of terminology, a lot of statistical tests, a lot of things that I don't even use within my analysis because they're very complex. And so there are a lot of statistical software out there that make it possible for you to run these analyses. But again, it's just going to run what you tell it to do. And so they still required you to have some sort of knowledge of the tests in order to ensure that you're running the accurate tests and interpreting them. And so they should really only be used when necessary to answer the research question, and I encourage you to use statistical consultants when trying to conduct more complicated analyses. So that is it on chapter 31 on regression analysis.